Um, well, yeah, no, it was 13. And then yeah, no, that's correct. Okay. 128, 100, 256.
There it is. You did it. No, you don't need to add 1024.
Why? No, the 512.
Oh, that's my mistake. 512 doesn't get involved. Because... Because if it were there... Okay, let's write it but cross it out. 5, 12, and it's not there. Cross it out. Because... this is the place that is responsible for 512, and it's a 0. There's no 512. We stop here.
But I got 507.
Yes, precisely. You got the answer.
Why did I get 507? I thought it was 500.
Because if you come back to what we did over here, upstairs, we added 7 to the 500 in binary. That's what it means. It's the same.
Why did we add? Why did we add to it then?
It was just an example. We just added these numbers because they were here. Those are the two random numbers that you came up with, right? And we translated
I added
them
500 and I added
binary
7,
code.
yeah.
Then we added them.
Oh.
And then we translated them back into normal
numbers. I get it now. I think I get it.
That's what you did.
I understand what happened.
The reason why we use binary code is because it's really easy to do with computers.
You're able to send a lot more over you're able to send more information over with less.
Yes, precisely. And with numbers like this, there's no such thing as a 2. There's no between state. Electricity is either on or it's off. Well, if you're dealing with radio, not quite, but when it comes to the computers that are easy to make, it's either on or
5,
off.
5,
it's 1 or
10,
a 0.
1, 1.
That's it.
5, 5 for the 1, 1. Just the 10 and the 11. And then the 1 plus 3 plus 4 plus 16. And then this one is separate because that was the word that wasn't erased. And then a 7 for adding for the original 2. So these two right here are this. And this is all this. is right here, which goes up to 7. To be 500 is the 7. Okay. And then this is where it gets translated back into this. Which it goes to the 507. Yeah, I was recording that part just so I can remember it.
Oh, don't worry, I'm recording these too.
Hmm.
Well, some of it.
I didn't even know you were recording it.
So, and your way of using 5s to understand it makes sense. Technically, 5 doesn't get involved at all.
No, 5 doesn't get involved at all, but the 1 is a 5.
I'm glad that
In
it helps you
disguise.
understand.
5 is a 1 in disguise. And so the 1 1 makes 10, which means it's just a 5 mimic. Which is a silly way of seeing it, but if you think about it, I mean, if the 1 and the 1 normally makes 2, but actually now makes 10, that means it's just 2 5 trying to be 10, but they're 1s.
So, that is... Yep. That's what a number system looks like. There are other number systems that you can use. A common one that's also used with computers is hexadecimal, which is where instead of counting by tens, you count by 16s. I can't quite explain why this is easy to do with computers, but it works well with binary code, which is what you just did. The thing I sent from work is what happens when we start counting by prime numbers instead of these nice, neat powers of 2. So, where's my pen? I left it over here somewhere. Here. What happens if instead of these, we use 1, 2, 3, 7, 11, 13, 17, I think is next, 19. These are prime numbers. There's no other way to get them than by inventing prime numbers. That's what I'm trying to bring home from work, is this insane theory that it might be possible to do math with this number set. Now don't think too hard about it. I shouldn't think too hard about it. I thought really hard about it and left it on some foam tablets. So, don't worry about it.